students, welcome back to our course Environmental Modeling and Simulation. In today's lecture, we are going to discuss groundwater extraction, which is basically extracting the groundwater for our use. Now, when we extract the groundwater, we have to be very careful that we don't extract it too fast in a way that it disturbs the equilibrium. What I mean by that is, let's take a very simple system. Without knowing whether it's a confined aquifer or an unconfined aquifer, let's say this is the ground level and this is the impervious surface below the aquifer, regardless of whether it is confined or unconfined aquifer. And then here we have dug our well or our tube well, and we are extracting the water at the rate Q. This is the water table in the well. Now, the reason why there is water in the well is because the groundwater inside the ground is pouring into the well. Now, the movement of groundwater through the soil into the well will be governed by Darcy's law, which we have already covered in previous lectures. Now, here's the thing. Following the Darcy's law, the groundwater is moving into the well, which is the inflow. We are extracting the water at rate Q. If inflow and Q are equal to each other, the level of water in the well or in the tube well will be at equilibrium. The rate at which we are extracting the water, which is Q, is higher than the inflow, then the water table in the tube well will fall down, which is not what we want, because then our well is useless, it has run dry. So, depending upon whether it's confined aquifer or unconfined aquifer, the flow of water into the well will vary, and it is very important for us to figure out the extraction rate which should be permissible under given circumstances, so that the well does not run dry, or we are extracting too little and we are not making the most benefit out of it. This is where the modeling comes in, and it's a very simple modeling, and we are going to see how it works. So, whether it is a confined aquifer or an unconfined aquifer, the approach is same. We use Darcy's law. So, if you remember, Darcy's law says that the flow of groundwater, which should be equal to extraction flow, so inflow, is basically the coefficient that we had, and then the hydraulic gradient, which is driving the movement of water, and then the area. Now, here if you look at the diagram I have drawn on the left, it appears that the water is moving in horizontally and radially. Horizontally because you see the lines are horizontal, they are parallel to earth. Radially, if you look at the top view, this is your well and the water is moving radially, which is a good assumption to make, but it's not always true, and we'll see about that later. Now, the reason why water is moving is because there is pressure head, there is pressure difference. So, let's say the water table here is here. So, this is showing you the water table, and this is the water table here in the well, and between these 2 points we have a gradient. Since the water is being drawn, we have talked about this in past, the water table will dip near the well. And this typically it works radially. So, the height here, let us say Hx, at a distance Rx from the center of the well, and if you go Rx in other direction, the height should also be Hx. Yeah, so it is a radial caving of the water table. Now, this pressure gradient is what drives the water flow into the well. So, we know here that dH by dr is basically the difference in the height. A here is the area through which the water is moving. So, here let us say at Rx distance the height is Hx. Yeah. So, from the view that we are looking at the top graph, it looks like two vertical lines. From the top view, which is at the lower graph, and if this inner circle is your well, this is Rx. So, distance Rx from the center of the well, this green circle here has the height Hx in the water table. So, the surface area of this cylinder, the green cylinder with height Hx and radius Rx is the area through which the water is moving in. Right. So, now we can separate the variables and integrate them. Let's bring R on the left hand side. Okay, now let me explain to you what the limits of integration here are. So, if you look at diagram on the top left, here I am assuming an unconfined aquifer. So, an unconfined aquifer is not confined on the top and there is nothing that is pushing the water down. The actual head of the water represents the pressure head of the water. So, it is very easy to calculate this in this situation. Now, the radius of the well itself is RW, the small r, right, because in the well itself the water would be flat, it will not have a gradient. So, the gradient starts from RW distance. So, the radius starts from RW. After a particular distance, long enough distance, the height of the water table will stabilize. There are a lot of assumptions in this and I will tell you what the assumptions are again. More assumptions I will tell you. I have only told you that the surface is homogeneous, the flow is horizontal and radial. The other assumption is that the water table without the well is horizontal, which is not always true, especially in hilly areas or areas with uneven terrain. So, after some time, since we are assuming that the water table is horizontal, the water table will reach its original horizontal height, which is, let us say, capital H. And the distance when it first does that from the center of the well is capital R. So, we integrate from RW to capital R and from HW to capital H. What is HW? HW is the height of the water in the well. Clear? So, we are going from the well to the place where the water table is no longer affected by extraction of groundwater. That is the integration we are doing. Now, this integration works very well for unconfined aquifer. Notice we have just used Darcy's equation, that is all we have done. We have already discussed Darcy's equation in past, so I am not going to go in detail. In a confined aquifer, the system will look slightly different. Let us take a look. So, let us say this is our ground level and this is the bottom impervious layer. We have another impervious layer here, which is not necessarily ending up with the ground level. You know, there might be another pervious layer between ground level and the impervious top layer. Now, it is in this between area where we have aquifer. Now, if this aquifer is linked with the higher pressure head for some reason and it is under pressure, this is also going to result in what are known as Artesian wells. So, Artesian wells typically always come out of confined aquifers that are under pressure. If we dig this portion and make a well here, so we have made a well through the pervious and the impervious top layer, the water table to the left and the right side of the well is going to be same as the height of the water table, right. So, here there is a drop in the height of the water table, here there is no drop because water is already under the pressure. The actual pressure head of the water may look very different. So, if you look at the pressure head, it is quite possible that here this is your pressure head and then here this is your pressure head. And obviously, there is water in the well, the water is still here. So, you see the actual water level is here, but the water pressure head is here. That is the difference between unconfined and confined aquifer when we are modeling. The difference it makes in our integration is very simple. Our Q is still equal to K dH by dr A. Since the movement of the water is driven by the gradient in the pressure head, not necessarily water table, sometimes they are coincident, sometimes they are not. We are going to understand dH by dr on the basis of the red line, the contour of the pressure head. So, the area will look at this capital H, which is the height of the water table, but dH by dr, the H in this is the height of the pressure head. So, Notice here we had h, here we had h. So, when we separated the variable, we got h dh. In this case, what you will get is integral of dr by r from rw to capital R, which is where the pressure head becomes horizontal. This is again same rw, and this is capital R, this is capital H. You will get is 2 pi k by q. Capital H will come out, and then here you will have, because capital H is the height here, so it is constant, it will come out, and here you will have just dh from height in the well to the height, maximum height of the pressure head. Now, the difference once you have integrated is, in the first case, which is the case of unconfined aquifer, you are going to get a solution that has h square in it. In the second case, which is here, you are going to get h linear, h to the power 1, right. This is a confined aquifer. Okay, let me just clarify. This pressure head surface, the technical term for it is piezometric. Okay, I think there is no point integrating this. At this stage, you know how to integrate these, so you can do it yourself. Just listing out the assumptions once again. The assumption is that permeability is homogeneous of the soil itself is homogeneous. Another very important assumption that I have made here is that your well is completely dug. Your well has been dug to the bottom of the aquifer until it reaches the next impervious layer. If this is not the case, you are going to get less inflow, so your Q value is going to be different, and for that you have to add a correction factor, and I will write down the correction factor in a bit and show you what the correction factor looks like. Alright. So, this is another very important assumption in this model that we have looked at, which is that the well is completely dug, it is not a partially dug well. Next is, as I mentioned, the water table is horizontal. Now, it is very easy to violate any of these assumptions. If you violate these assumptions, you have to rewrite the model. How will you rewrite? Let us say your pressure head is not horizontal, then you are talking about a very different dH by dr, and you need to account for that in this part of your equation. Let us say your soil is not completely homogeneous, the permeability is not homogeneous, then you have to modify the Darcy's equation itself. So, depending upon the assumptions that are not applicable, you will have to modify this model. Let us look at what happens when our well is not completely dug. So, again we have confined aquifer, unconfined aquifer, and in both cases we have correction factors, and I am going to write the correction factors. Confined aquifer, incompletely dug. Now, the technical way of referring to incompletely dug well is partial penetration of an aquifer. Alrighty. Now, why do we need a correction factor again? Let us take a look. So, let us say you have an unconfined aquifer, and this is the impervious bottom layer. It is an unconfined, and you have an incomplete well. It is not completely dug, it is partially penetrating the aquifer. Now, what will happen is that, remember, one of the assumptions of our previous model was that the flow is horizontal and radial, which will be the case for some part of the well, but towards the bottom of the well, the flow is no longer horizontal, and we need to account for it. For good part of the well, it is horizontal and radial, but for the bottom part, notice here, no longer horizontal, no longer radial. Well, it may still be radial, but definitely not horizontal. Artesian aquifer, artesian well. So, in case of incomplete penetration of the aquifer or partial penetration, we will multiply the flow rate with the correction factor, because the flow rate now, inflow rate is different. So, the correction factor, and I am going to give first for the confined aquifer and then for an unconfined aquifer. So, for a confined aquifer, correction factor F will be alpha into 1 plus 7 radius of the well. D1 is the depth of the tube well into the aquifer multiplied by cos pi alpha by 2. This is the correction factor. So, H1 is the height of the confined aquifer. Let's say if this is the diagram, we convert it into a confined aquifer, then this is the scenario we have. Let's say this is the upper confined boundary, right. So, this is an artesian well, the flow is happening from the bottom, and let's say this is the height H1 of your aquifer. Now, alpha is a new ratio that we have introduced, which is D1 by H. So, D1 here is the depth of your tube well or your well into the aquifer to the total height of the aquifer, which here is H1. If you put this information here, you will get your correction factor, and your Q value needs to be multiplied. So, your Q dash, your effective flow, will be correction factor into your actual flow if this was completely penetrated tube well, actual flow that you will get from here. So, this is confined aquifer. Now, the correction factor for the unconfined aquifer looks very similar. So, I am going to do that in the next slide. Unconfined aquifer. The correction factor for unconfined aquifer, again to be multiplied to the flow rate Q, is given by alpha into 1 plus 7 root radius of the well divided by depth of the well into the aquifer multiplied by cos by alpha by 2. So, instead of H here, we have D1. That is the only difference between the formula for confined and unconfined aquifer. Remember, I do not require you to memorize this. So, if we do ask a question, I will give you the formula. So, do not have to memorize this. But it is important to note that if the well does not go all the way down into the aquifer, then the assumption made in this particular model that the flow is horizontal and radial is no longer true, and because of that we have to introduce correction factors. Okay. Now, there is another situation where we barely enter the aquifer. So, here it is, I mean, I showed it like it is barely entering, but still there is some amount of tube well that does enter the aquifer. Now, what happens when the well barely touches the aquifer? In that case, we have a well like situation. So, we are going to talk about spherical flow in the wells. So, let us say this is our land ground level and this is your well and this is your bottom impervious layer. So, we are dealing with an unconfined aquifer. So, let us say this is the level in the well and the piezometric surface looks like this. So, if you look and this is your water table at sufficient enough distance. So, the actual water table without the well. Now, notice one thing, that this tube well is barely dipping into the aquifer, into the wet part of the aquifer. So, the flow is barely horizontal, it is more spherical. So, we are dealing with the spherical flow in the well. So, the flow is basically like this, it is like a sphere. And then here we have the height of the sphere, the flow would be horizontal, but here we have the height of the sphere. And this part is unconfined. So, when we are dealing with simple radial flow, again we have to either have a correction factor in our flow rate when we are trying to match Q is equal to inflow, or we need to model it separately. And there is a correction factor that we use, and what you need to know is flow rate in a spherical well proportion to the flow rate if it is completely penetrated and we only have horizontal and radial flow is equal to RW radius of the well divided by height here H natural log R by RW. Here the assumption is there is no horizontal flow. Okay. Now, the next thing that I want to cover is what happens when we have multiple tube wells or wells in the same aquifer close to each other. So, let us say this is the ground level and we are talking about unconfined aquifer. So, here we have the bottom impervious layer, right, and then this is our first well, again we have drilled completely, second well, which is, as you know, typically the case in our modern day civilization in India, where so many homes rely on groundwater for meeting their water needs. So, now what is going to happen is that the water table here in each well is going to impact the flow rate Q1, Q2, Q3 that is okay for each home or each well to withdraw will affect each other. So, we have formulae for what to do when you have two wells next to each other, not the third one. So, we hide the third one, only take two at a time. So, we have a formula for that we have calculated. What we need to understand is that the distance between the well is going to make a difference. So, let us erase the third well for now and let us see how the piezometric surface may look between these two wells. So, here it is definitely going to go like this, where the water table is, and same is going to do on the left side, reach the water table. Now, between them it will try to reach the water table and it may or may not reach, but then it is going to see another dip. So, now on this end, on the left side of the first well, we still are noticing the drop that we saw in previous model, and same thing is true on the right side of the second well. But between the two wells, we are seeing very different drop. So, we will have to specially account for the flow rate here, and of course, it will again follow the same principles, the Darcy's law, and again we want the net inflow towards this fully penetrated wells, horizontal and radial inflow, to match the output, the extraction of the water, and this is relatively simple. Now, bring in the third well. A third well can come in multiple ways. So, let us say they all come in a line. Now, once again here also we will see a difference. This is not going to match what is going to be on the right side. So, we need to account for that. Now, from the top view, what this is looking like is we have a well here, we have a well here, we have a well here. This situation is different from when you have wells in a triangle. Again, not only the relative location of the well is important, but also the distance between the wells is important. So, here let us say we have an equilateral triangle. This is still relatively symmetric and relatively easy to calculate. I can give you the formula, but there is no point calculating it, because when we do dig our tube wells, we do not arrange them typically in perfect line or in equilateral triangles. So, there is no point for you to memorize or keep note of formulae for strictly choreographed location of tube wells. What you need to understand is that, much like what we discussed when we talked about air pollution flow through a chimney, through a stack, and that when there are multiple stacks available, these plumes are going to interact with each other, they are going to overlap, and we have to look at their cumulative response. And depending upon their distance from each other, the distance between the chimneys, the relative position of the chimneys to each other, the concentration of the contaminant that we are targeting in any location would be different. Same thing is happening here. We know how to model how the water surface falls down at a well when we are extracting water. We know how to figure out at what rate to extract the water so that it is sustainable. Now, when we bring more wells, we have to look at how these wells are interacting and affecting the water table between each other, because here the maximum height that the water table will reach will be less than the maximum height that it will reach when there is no other well next to this particular well. So, here the difference in the pressure head is going to be higher here than it is going to be here. The inflow of water from the left hand side of the third well would be less than the inflow from the right side of the well. So, the net Q rate will reduce, the Q that is sustainable for this well will go down. Now, as water engineers, water supply engineers, environmental engineers or modelers who are tasked with figuring this out, whether it is for water or for petrol extraction or any kind of extraction, basic mathematical concepts that we have studied still apply. We are still going to use Darcy's equation. Once we figure out the height here, we are going to be able to figure out the del H. We are going to be able to figure out the distance from the center of the well to where the water piezometric surface peaks between the well. And this might require some computational modeling on computers to do a better job. You can also do it by hand, but that's going to be more complicated. So, the take home message is, when we are extracting the water, take home message for this lecture today, when we are extracting the water from the ground, the rate of extraction should match the rate of inflow into the well, which is going to be different for confined and unconfined aquifer, because in unconfined aquifer, the piezometric surface matches the water table. That is not typically the case with artesian wells, which are confined wells. Next thing was that we learned if tube well or the well does not permeate, does not penetrate the aquifer completely, we need to account for correction factor, because now the flow is no longer horizontal and radial. Next thing we learnt was, when the well barely touches the water table, the flow is not at all horizontal and radial, and we need to account for spherical flow of water. The last thing that we discussed today in the class was, when we have multiple wells in the vicinity of each other and the withdrawing water or whatever fluid you are withdrawing from one particular well is affecting the head available to the other wells, it is going to affect the net flow rate that is permissible from each well, and this needs to be accounted for. In this case, there are two things that matter. First is the distance between the well, and second is the relative position of the wells. Alright students, that is all for today's lecture. Thanks, and see you in the next lecture.